Hello everyone, this is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I am dealing with the course Computational Aerodynamics. And today's topic we will see discussion on definition and terminology for the module 1. Okay, so basically we will see what is definition terminology in the module 1, and also we'll discuss the insights of other modules also regarding the definition terminology. But basically the base for the CAD is module 1, so where we define different types of control volume and flow properties. So these aspects are available actually. So therefore we'll just see the basic terminology of definitions in the module 1. So here in the module 1, so we have the major topics as the defining the flow variables. So we have flow variables. So we need to define the flow variables. Then we have to define different types of control volumes. So control volumes and fluid element approach actually. So fluid element. So we have fluid element approach. Then after that we will have the governing equations. So we'll have governing equations. Then we have shock capturing and shock fitting techniques. So with this, these are the major topics which are available in the module 1. So here for the definition terminology, so first we need to see basically what is a flow variable. So what are the flow properties available for the fluid flow actually. So that is the first thing which we need to know. So what are the flow properties which are available for the fluid flow? So the flow properties basically they are pressure P. Okay, so pressure P. So pressure P is an intensive property. So basically irrespective of size or let's say shape. So the basic let us take a tank. So if you have a tank of let's say 1 meter square or let's say 1 cubic meter volume, and let us say you have a tank. So let us take your other tank of which of let's say 5 meter cube. So let's say you have this case. So in the 1 meter cube tank and in the 5 meter cube tank, you can have same pressure. It's not like you have 1 meter cube tank, you should have high pressure. You have 5 meter tank, you should have low pressure. No, it's not like that. So since pressure in intensive property, so the formulation of pressure is force by area. So which is nothing but Newton per meter square. So these are the units of the pressure actually. So we can say, so from this, so pressure for less area should be let's say it's high, and pressure for the more area it should be low. So what is happening actually? So here pressure is an intensive property, so it does not depend on any quantities. So irrespective of the shape or the size of the system, so the pressure actually will depend on, like it does not depend on any property. And whatever the tank you have, whether it is a low area or high area tank, or low volume or high volume tank, so since it is an intensive property, you can have same pressure which is of 1 atmosphere. So let's say you have pressure 1 atmosphere. So here also you can have pressure as 1 atmosphere. So this is the one of the primary flow variable for the fluid flow properties. So here the major aspect of pressure is, so it will govern the fluid flow. So govern the fluid flow in the sense, so it will accelerate or decelerate the fluid flow. So fluid flow will start from certain region to another region. So because of pressure difference. So let us take this is a station 1, and let us take this is station 2. Okay, so the fluid, if it has to go from station 1 to station 2, so P1 and let us take P2. So if P1 is greater than P2, so let's say what happens? So the fluid will always flow from higher pressure to lower pressure actually. So from here to this point, so the fluid will flow actually. So from P1 to P2, so let's say from one station to other station, fluid will start propagating from 1 to 2. Okay, this is the scenario. So when the vice versa, so let us take P2 is greater than P1. So when P2 is greater than P1, what happens actually? So the reverse flow will happen. So the axis system what we have taken is like, let's say P1 should it is a starting point and P2 is ending point. So when the pressure P2 is greater than P1, so what happens actually? So the reverse flow will come actually. So the pressure, whatever on the left hand, right hand side. So let's say you have this P2. So this is more, and you have the reverse flow phenomena, and it goes to 1 actually. Okay. So this is what we have. Next, then you have temperature. Then you have temperature T. So other flow property, so is temperature. So since temperature, so is a measure of degree of hotness or coldness of any material or flow you take. So this actually is also an intensive property. So the temperature also, you can take a fluid. So let's say same again the example. So we have 1 meter cube tank. So we have another tank which of 5 meter cube tank. So whether let's say you heat here, okay, you apply some heat, again you apply some heat. So irrespective, let's say you have a water here, so you have a water here. So whatever the temperature it achieves, it is also achieving actually. So initially, let's say the tank is at 20 degrees Celsius. So this is also 20 degrees Celsius. So maybe you have a large quantity so of water in this tank. So time taken for this one might be high, like low. This might be high, but irrespective of that, so whatever the temperature that it can achieve, so this tank achieve, this can also achieve. Let's say it is increased to 100 degrees Celsius. So the 100 degrees Celsius same can be achieved by both the tank, like tank 2. Okay. So basically, what I want to say is that, so whether it is a large tank volume or a small tank volume, so the temperature, since it is an intensive property, so the temperature can increase or decrease irrespective of the size. Okay. So there are three modes of temperature heat transfer. So basically, you have conduction, you have convection, and you have radiation. So basically, the conduction is because of the molecular collision between the solid particles. So this happens. So the convection, this happens because of the wall temperature and the free flow surface. So that is the convection, and the radiation is the one so which happens because of any other like influence of like the sun or other planets. So let's say you can take in that way. So these are the some of the examples of the radiation. So the temperature, irrespective of the size and the shape of the volume of any system you take, so it does not vary. Okay, so that is what temperature. So next one we have velocity. So previously we discussed about pressure and temperature. So basically this pressure and temperature, they are scalars actually. So basically the difference between vector and scalar is, so vector has both magnitude and direction. So scalar does not have any any like direction. So it can go in all the directions. Like we will define only magnitude for the scalar. So here the pressure and temperature, so both are scalars actually. So now we are taking velocity. So velocity v is a vector actually. Okay. So velocity v is a flow variable. So which we have to define. So direction and the magnitude. So if we write the position vector, so v bar is equal to, so u of I cap plus v of j cap plus w of k cap. So this is a position vector. So let's say this is a vector quantity entity for the velocity. Okay. So what is the meaning actually? So this capital V is function of small u and let's say V and W actually. Okay. Now basically this capital V, what we are talking is a vector entity, so which depends on the magnitudes of u velocity and V velocity and the W velocity. Okay. So now we have discussed another flow variable, so which is velocity. Next, so we have another flow variable which is density. Okay. So density now it is a scalar actually. So density, so we have basic formulation, mass is equal to density into volume. So density is equal to mass by volume. From this, like, we will get to know. So what is this? So the unit for mass, let us take it as kg. So unit for volume, let us take it as meter cube in SI system. So basically the density is expressing, so how much amount of, like, how like what is the amount of fluid particles it contains per unit volume. Okay. So density of the flow will actually discuss about the amount of matter which contained per unit volume. So this in this way we can actually express it as. Okay. So the primary flow variables which the, or the basic flow variables which are present for the fluid flow are, so basically pressure, so temperature and velocity vector and density. Okay. So these are the primary flow variables which are available. Now these primary flow variables, they are actually depending upon uh, two entities. One is called time, other one is space. So therefore, so the pressure P is function of t comma x comma y comma z. So the pressure is function of t x y z. The meaning is, so the pressure varies with respect to time and with respect to x coordinate, with respect to y coordinate, with respect to z coordinate. Okay. So let us take an entity, so three-dimensional entity, and you will get to know. So let us take it as x-axis, y-axis, z-axis. Okay. So let us take this as a particle, fluid particle. So this fluid particle, it has to travel from one point. So it is traveling from one point, and it has achieved at other point. So this is point 1 and this is point 2. So when it is traveling from point 1 to 2, so whatever the changes that happens for the pressure, for the temperature, for the velocity, for the density, so we need to report it actually. So that is what majorly deals with the aerodynamics, or let's say it can be high speed aerodynamics, it can be low speed aerodynamics. So these aspects are present actually. Now what we have, so basically the pressure is a function of temperature x y z. So let us take the flow variable pressure p1. So here, so when it is going from p1 to p2, so whatever the variations we have, so with respect to time, so if we have variation with respect to time, so we need to report p as function of t. And if pressure varies along x direction, so in this direction, if the pressure varies, so then you have to write down along x direction. If it varies also along y direction, you have to report it. So if it is only 2D, so no need to take z, so we can stop it. So t comma x comma y. So if it is 3D, so since if it is varying along z axis also, so you have to write p is t comma x comma y comma z. So this is what we have for the basic entity of the fluid flow variables. Okay. So with this we have seen the first question of the definite terminology. The second one, so basically we will see the basic entities of fluid flow, how what are the approaches, and how do we model the conservation equations. So what are the different types of fluid element approach, we'll see. So basically you have two types. One is control volume approach, which is CV, Other one is called fluid element approach. Other one is called fluid element approach. So, and in this you have two subdivisions. So in the control volume, so basically it can be stationary, it can be movable actually. So if the control volume is fixed in space, so whatever the governing equations we derive, so basically they are called conserved form of governing equations. So if the control volume is moving with respect to let's say space, so we derive non-conservative form of equation. The physics of the flow does not vary, but so what we are doing, so we are making the control volume stationary initially, and we are making the fluid flow through the control volume. So if you take this as a control volume, so this flow is coming inside, this flow is going outside. So this is in and this is out, but this CV velocity is zero. Okay, so CV velocity is zero. So here what is happening actually? So example you can take of our house taps. So our taps, they are stationary, they will not at all move. So when you open the valve, what happens actually? The water from the tank will come through some channels and it will release through the tap. So you can take the tap as a control volume. So where the fluid is coming inside to the tap and it is leaving the tap surface actually. So that is one small example which I am telling. So where the control volume is stationary. So whatever the governing equations we derive for the control volume which is stationary. So whether the control volume is stationary or control volume is moving, so we derive governing equations, conservation of mass, conservation of momentum, conservation of energy. So irrespective of any type of conservation, sorry, any type of the volume. So whether it is stationary, whether it is moving, but the physics of the fluid does not like change. So here what is happening actually? So when you are taking the control volume stationary, you will not consider any velocity of the control volume. So when you take the control volume is moving with respect to space, so let's say it is moving with the flow. So CV has some velocity of VCV. Okay. So and this is the velocity of the fluid. So the relative velocity between the control volume on the fluid has to be taken when you derive the governing equations. So that is the difference. So when you have the control volume which is stationary, so we have when you have the control volume which is stationary, we have CV is equal to 0. The fluid comes in, the fluid goes out. So when the control volume is moving with respect to space, or let's say moving with respect to the fluid flow, so whatever the fluid velocity it has, let's say that relative velocity has to be taken to derive the governing equations of continuity, momentum and energy. So we have another approach which is called the fluid element approach. So you take a fluid particle. So for this fluid particle, so again you apply, so whatever the fluid which is crossing, or let's say number of change of molecules that is happening when this fluid enters and leaves actually. So you take a molecule or an element approach. So where you derive the governing equations here in differential form. Here you derive governing equation in integral form. That is the difference. Here we derive equations in integral form. Here we derive equations in differential form. Okay, so that is what we have for the fluid element approach. So here another is, so let's say the fluid is actually moving with respect to flow. So here whatever the approach we take for deriving the governing equations, so is one is moving with the flow, other one is stationary. So when it is moving with the flow, so what we take? We take the relative velocity. When it is stationary, we actually does not take relative velocity. We will take the absolute, or let's say we take the whatever flow velocity we have. So another realistic example is, let's say, aircraft engine, so which is attached to the aircraft. So if you take aircraft engine as a control volume, so what happens? The engine also has velocity what aircraft has. Flow also enters and flow also leaves. Okay. So therefore, whatever the relative velocity that we need to account when we derive governing equations. Okay, so this is one of the aspect of definite terminology. So for the model 1. So with this, we have seen some aspect of the definite terminology of the module 1. So in the next session, we will see the definition terminology of the other modules. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.